Well, hi, good morning. Thank you for joining me in my shop here. Today is the 10th of May. Another sunny day coming today. And I'm almost finished dealing with all the tree fall, all the branches that fell during the ice storm about a month ago. Seems like forever ago. Which ended up with a lot of broken wood in my backyard. So I'm almost finished chopping it all up. I just have the big stuff now. Maybe I can get it on camera later. I'll show you the pile that's out there still. Well, that's the good news. On the radio here. So I think my intention at the end of yesterday was to switch to doing an alignment at this point. But you know what? I think there's still some capacitor work I can do here, which makes some sense before doing the initial alignment. And thank you very much for reminding me about the other grid blocking capacitor that's in this radio. Quite commonly a radio like this, there's only really one grid blocking capacitor, and it's at the output tube. But this one has two audio tubes, and the first audio tube also has a grid blocking capacitor, and I kind of forgot about that. So we're going to repeat the leakage test, see if it's leaking, replace it if we need to, and then we're going to identify one or two other capacitors, maybe the AVC capacitor or one that's involved with screens. Try to find those and replace those before doing the alignment, and that might leave 3 or 4 older capacitors still in here, but that's going to be okay. So first thing is the leaky capacitor test on the 6SJ5. So let's just take a look at the schematic here. Okay, so this is the capacitor I convinced myself is okay, along with this one, both having been replaced by somebody, and they seem to be holding up fine. This is the one I forgot about, and we could include a few more in this. I've heard the tone control, so I know this is working. This is a 100 picofarad, so this is probably a mica. You shouldn't worry about that. This is the only one really to worry about. So C25, where do we go to C25? Right here, easy to find. So I'm going to look in the radio here using the map. Oh my gosh, it's pretty easy to spot. It's a great big thing. Am I absolutely right? Yes, I am. Okay, I know which capacitor it is, so I know which one to test now. Did I say, oh, it's a great big one? It's just a regular wax capacitor. I was a little dramatic. There's this guy here. So we'll test them on either side. Okay. Turn on the radio now. Turn down the volume. Meter. Okay, it's still grounded to the chassis. Set this back to DC. Ooh, did I make DC tests on this with this thing in the wrong position? I may have. Maybe it's with all the crackling here. Okay, so I would say let's just check both sides. Here's the resistor that I changed right here. Whoops. Good thing you weren't looking at the meter when I did that. I had the meter set to 1.5 volts. I really whacked the pointer there. I'm going to bend it if I do that too many times. There we go again. So 150 scale, we're about 90 volts here, and I think I'm way low on the supply. No, I'm not. 116, not low on the supply. And the other side of the capacitor, capacitor with the same voltage on both sides. Let's look at that on the schematic again. The schematic. So we're talking about this capacitor right here. It should have plate voltage on one side, and on the other it should be nothing. Wow, that's bad. That's really bad. Is that, if I got the right capacitor here? Because that's a whopper leak through. That's almost a short circuit, in fact. C25. So C25, I'm going to do it by terminal here. This is the capacitor. Yeah, it's the same one with the resistor I changed right here. So I'm on the right capacitor. What is this terminal up here? It's coming from, this would be the plate terminal up here, and then the signal comes down here, and then this I think is probably a grounding point. Looking all over the place, and a lot of wires coming to it. I don't know. Doesn't look like a grounding point if it's coming from here. Oh, look at these voltages. No, that's the rating. That's the rating voltage. If you can hear some shoveling sound in the background, that's a cat in a litter box quite a ways from here. Well, I think this guy's really bad. I think that's all you can conclude. It's driving the grid up, way up. That would pretty much wreck the operation of this radio, though. I can't believe it, what I just tested. I'm doing something wrong. Let me go back and test it again. Okay, I must be doing something wrong. Often when you do these tests and you go to read the grid voltage and it's high, as soon as you touch it, it starts coming down right away because the charge is so weak, you're bleeding it off through the meter. So that's got to be here. There's really no two ways about it. That's 75 volts positive on the grid. Okay, we're gonna get rid of that guy. We'll take this guy out and test him. That's a really, really bad showing. That's like one of the worst I've ever tested. Can't believe the radio would still work. Okay, I should be able to remember this terminal. Pretty crowded over here. Trying to cut the one wire you want to cut and not one by accident is not the easiest thing right in here. There you are. 0.01 600 volt. Let's try this test. This quickie test here. If it's shorted out, well, it'd be interesting to put an ohm meter on it. Can it be that bad? It could be totally short. Could be. Trying to explain how the sound's getting through this. 17 nanofarads. 17 nanofarads it's reading. That's not at all, that's just not at all what I expected there. Not in the least. Maybe I didn't make good connection to the wire, so let's try it on the classic capacitor checker here. Gotta take a day off and just clear my bench of junk that's building up all over the place here. So if you're not familiar with this test, this device will put DC voltages on the capacitor, and then it has a very sensitive way of showing a tiny current flow. So using this magic eye here, if there's any current flow through the capacitor once it's finished charging, the eye will not be open like you sort of see it now. It's a little hard to see it, isn't it? But you can see the pie is open at the bottom. Here we go. So that tested perfectly good. So 150 volts. So I'm at 150 volts and it's showing the eye is staying closed. This is typical of capacitors of this sort coming out of a radio of that age. But nanofarads. Wait a minute. Let's use this device to measure the capacitance here. 0.01 should show up here. You can watch the eye now for it to pop open. There's a little something happening there. You probably can't see it. And where is that? So on the 0.5 to 0.001 scale, that's this scale. 2. Get out of here. Okay, so if it's actually nanofarads, go down here, it's not going to open at all. Oh, it does open, but that's, you get close to the end of the run on this device, then often it opens anyway. So I don't think that's valid. I think the answer is whatever the capacitance is, this device can't really measure it. See, it's opening again right at the extreme. Yeah, no measurement possible. What is going on with this capacitor? So in the radio it showed a leak of 100%, almost 100%. On this electronic tester it said there's no capacitance left, which usually indicates a broken lead, open lead. On the other capacitor checker, it says this capacitor is just a typical capacitor from an old radio, but it should not, I don't think it was leaking bad enough to show that high voltage. Maybe I'm not, you know, a lot of these tests are kind of qualitative and just based on experience, my experience. It's exactly the same, 18 nanofarads. 18.35 nanofarads. That V loss number is kind of high too. Well, I don't know how to explain that. Usually when a capacitor is leaky, I find these, when you measure the capacitance with a device like this or something, that you get a high reading, higher than true. Okay, well it's out now, so we'll put a new one in and then we'll repeat that voltage test. Find out what's going on. 0.01. We'll stick one in there. Okay, so you can see the nice yellow capacitor right here. That's the guy we're going to test again. I'm very, very curious about this, because for me it's a surprising. Those are cats running around above us. Oh, running around behind us now. Racing around through the house. Okay, you're ready now. You can see the meter. No, you cannot. One side. Other side. I got this all turned around. I've got this all turned around. I've got this all turned around. Well, I got it backwards. That's the 6SJ5. 6J5 there. This is the 6SQ7. I got it turned around. It's going from the plate of the 6SQ7 to the grid of the 6SJ7. Well, wait a minute. I mean, I'm still getting this crazy voltage reading there. So there's another capacitor right here. what do I got something going wrong here. Something's going wrong, and it's got to be me. So this is the guy. Here is plate on the 6SQ, so we read the plate voltage on one side. The other side, we're still reading the voltage. That, you know, that might mean this resistor is open, or this one. If this one were open, the radio wouldn't work at all because nothing get through. If this one were open, then the tiniest leak would charge this line up. You'd also have a potential leak this way, which would pull it down, and a leak through here, which would pull it down, but this leak would probably be tiny. I don't get it. Because we also have this, but it won't pull any DC down because of this capacitor, so it's really dependent on this resistor. We should measure the resistance of this side of the capacitor circuit to ground, and we should find 10,000 plus 470,000, about 500,000 ohms. We should find 500,000 ohms from here to ground. We also have, this is 1.5 million ohms this way, so, and it's a right to ground. Well, only through a capacitor. Ooh, that's an interesting one. Did I say this is volume? This is tone. There's the volume. Tone control. No difference anyway. Although, if you swing the tone control up here, you're applying a ground right on the other side of this capacitor, as opposed to on the other side of this resistor. Varying this control could identify a leak in this capacitor by varying the voltage up here. Let's do that for fun. I don't know, am I crazy? Sure. Sure I'm crazy. Okay, let's go back to the camera. Of course I'm crazy. We're all crazy. Crying out loud. Just we're all crazy in the same way. We can't judge it. Ask a cat. Cat will tell you if people are crazy. It's going to do the tone control on the voltage that shouldn't be there. So we're having the tone control. You know what, I'm going to use a clip lead here. On a live radio, not recommended. Famous last words. I don't recommend anybody do this. Okay. There we are. There's the voltage. The experiment is, does the voltage change if I fiddle with the tone control? Oh my gosh, it does. Very interesting. Okay, so I interpret that as saying the tone control resistor is a little leaky. But it shouldn't be any voltage there. Because the next thing is the resistor that's supposed to bleed that down. What is your problem? So there's a 470K right there. That'd be the guy. Okay, power off. What I'm going to do is I'm going to stop for a bit, make my cup of coffee up, and then we'll test that resistor. Okay, once again we must deploy the Allen meter. Bit of a tangle up there. This is supposed to be 270K. Should say 270, where it says 590. Well, I guess, you know, it goes high. It can't bleed down the charge as fast, but that's only double, you know. 600 instead of, well, it's a little more, it's about double, isn't it? Can't imagine that replacing that resistor is going to enable things to bleed down. That resistor doesn't seem to be going to a ground terminal. Where's it going? It's going to, oh, that's right, there's a resistor network here. Hey, let's poke around with the rest of the resistors. That's right. So it's coming to a terminal on the tube, but the terminal is spare. So it's just using it as a hookup point. So here's a resistor. It looks like, I don't know, brown, red, red. One, maybe 1200. Yeah, 1400. Okay, and then the other one looks like brown, green, green. No, brown, green, blue. That would be 1, 6, and a whole bunch. Like a really large one here. Really large one. That's 6, more than 6. No, it can't be more than 6. Can it? Can? Would it be? I can't imagine. 6 megahertz, 6 megohms rather. This thing is showing up at like 40 megohms. There's just no way. So what's going on there? So that's this guy. If you look, you see this is the first resistor that I thought might be open. And then this is the one that read 14 instead of 12. And then this is the one that's reading sky high. And it's brown, green, blue. So what would that be? That'd be one, that'd be like 16 with 8 zeros or something. What would that be? I don't know what that would be. Let's look upon the schematic once again. So we're dealing with this spot right here. We have a 1200 and the 500,000, which is reading, oh, 500,000. Wait a minute, 500,000. Wow, that's right. Okay, so you know what? That's reading roughly the correct amount. This one is out of control here. It's supposed to be 10,000. How do you get 10,000 out of 10,000? That would be an orange third band. That'd be a brown, black, orange. R13, but this is no brown, black, orange at all. It's way far from that. There's no brown, black, orange in the area. Brown, blue, brown, green, blue. So green is 5. So that's got to be 15. I don't know, 15 megohms or something crazy like that. Again, I just find these things and I think, no, Jim, you're just out to lunch on this stuff. You're looking in the wrong spot. You're being totally fooled. How can we prove this? So one side goes to ground, the other one goes back to here. It goes to this point, and the two guys are there. It's got to be this resistor. It goes to ground, eh? So I'm looking. Yes, that's a ground. How did that resistor get in? It's a weird looking resistor too. Let's take the weird resistor out of there, and we really should put in a 10K there. R13. There's a parts list. There is a parts list. So R13. Where are you? C. L. Where's the R's? Hey, who took away the R's? Coil? Capacitors? Here. What's this? Volume control? Tone? Oh my gosh, those cats are fighting. What are you guys fighting about? They might be playing I've got it, you can't have it. I think that's what's going on. Oh, there's the mouse. I see the gray mouse. They're playing I've got it, you can't have it. Oh, the mouse is free. Quickly, somebody notice the mouse is free. Guys, pay attention. Your cats, come on. Get the mouse. Never mind the other cat. The mouse isn't there anymore. Oh, there it is. Wait a minute. There's two mice. Okay, enough of that. They're wearing out anyway. The fight is wearing down. Okay. As soon as I moved, they relocated. Okay, enough of that. A little bit of cat excitement. Okay, now back to the resistor. Let's repeat the resistor test. Check the settings. Got to be on 60 megohms. I can't be wrong about that. Right to 0. This side is a grounded side, so if I touch the chassis, we should get a 0. There it is. Go across this resistor. Oh, it's charging up. This resistor might be open because that's a capacitor charging. Somebody's got to be open somewhere. How about you? Okay, we're gonna nip out one side here. We're gonna test it again. Well, yeah, I'm on the 60 megohm scale, and it's. Ooh, what was that? Where'd that come from? So the lowest reading I'm seeing there is 20. So I don't know what's going on here. It could be the maybe the leads go into these devices, and then they like a capacitor or a resistor. Then they got to make contact with the stuff inside, and that contact point is a point of weakness, which can give out. And then you can become intermittent, and all kinds of weird stuff can happen here. Let's take a look. What is happening? What do you say? 18 megohms. Brown. You know, it could be. Maybe this is 18 megohms. Because of brown, green, blue. But that's not what the schematic said. The schematic said something in the K range, 10K. Didn't I? Got to look at it again. Yeah, we didn't get anywhere down here, did we? That's right, I got distracted by EO cats. But go up here and we can find the resistor I'm talking about. This isn't a good way to do it. There, R13 right there, 10,000 ohms. Right to there. Ohms to here. Ground. Well, before I confuse myself any further, okay, 10,000 ohms. So we're going to put a 10,000 ohm resistor into this position and see what happens. How could this radio work? Okay, enough. Okay, I'm a little anxious about this because the size of that resistor is so far off from what it should be on the schematic. And you got to wonder, was there a bulletin on this radio? This is version number 3, and I got schematic for version number 1. For some reason they decided to put that whopper resistor in there, but it doesn't seem to make sense because of the voltage measurement I made. Okay, here we go. Voltmeter lead here, and here. And my messy bench. Okay, here we go. Okay. So we'll look at both sides of the capacitor. That's really how we can kind of identify the issue. So the start is the high side of the capacitor comes with almost 90 volts. The other side of the capacitor, this is the big moment here, much less. But still, a big voltage there. I mean, this is bad news. This is a big positive voltage on a grid. This doesn't make any sense to me. I got something more is going wrong here. Let me shut the power off. Listen to those cats. Oh my God, when they were kittens, it was just little pups. They just went whipping by there. Okay, I'm going to turn the camera this way just in case. There they go. One of them, anyway. What are they going to do? Yeah, he's heading for the litter box. I think that's where he's going. Hey, look worn out now, hopefully. Okay. Man, I don't run around like that anymore. What are we doing? We're looking at the 6J5 pinout to convince myself that the only explanation is senility. 6J. That's what I could be left with. Got to be careful here. 6J5. Come on, work the book. Well, it's a very simple tube, right? It's just a tryout tube. And let's look at what we got here. So the capacitor is going to the pin number 1, 2, 3, 4, 5. What is pin number 5? Pin number 5 is the grid. Perfect. Okay, so this grid is showing a positive high voltage. Still, there'd be something wrong with the tube. It's not very likely. So, okay, not much else to look at here. Plate is on 3. Why would I want to look at that? Plate is on 3. Yeah, there's a red wire going there. And the cathode is 8. And the cathode is 8. And there's the cathode is 8. And there's the 1200, 1400 resistor coming to it. I don't remember that. 1200. I don't remember it that way. Let's look again on the schematic here. Okay. I'm going to have to stop in a bit because I'm starting to lose it. So yeah, the 1200 connected to the cathode. So I measured this instead of 470, I measured it, what was it, 590. But the higher this is, the lower this voltage would become. How can this possibly be happening? If it's not coming from here, I don't know how this can happen. And is it real? The radio works. How can it work with a great big positive voltage on this grid? And you know what, Jim? How is this tube biased? It's biased with these resistors. Oh my gosh, what is going on in there? Something's being wrecked. Yeah, this is odd because there's no plate resistor, so it's all cathode resistor in here, and it's so this is part of probably why I'm misinterpreting this. what we should find is the cathode voltage is going up and down while the tube operates and the plate is holding still. Usually it's the other way around. So what? So this is connected to the cathode. I don't know. I'm not getting there. Look, if this is a cathode resistor, what do you mean if? It is a cathode resistor. Current flowing through it, this develops a positive voltage here, also develops a positive voltage here. And that positive voltage is being relayed right up to the grid. But the thing is, the volt, it's not, I know my mistake. I'm reading the grid to chassis. I should be reading grid to cathode. In this case, the cathode is wandering around. So I'm getting a false impression of the voltage relationship between the grid and the cathode on the assumption the cathode's at ground potential, but it's not. Okay, that's got to be my mistake. So I measure this differently. If I measure the grid voltage with respect to the cathode voltage more carefully, I should find a negative voltage here, or 0 anyway. Okay, that's been my mistake. Okay, but I got it. Let's check it out. Let's try it out. One of the reasons I do these radios, I'm retired, I could sit and watch TV all day, is I'm forcing my brain to think. I'm giving it something to chew on and forcing it to think hard. I mean, also I enjoy all this stuff too, but you know what, if you're trying to keep your brain alive and well, Sudoku is not going to do it for you. You need something more than that. Okay. Proper measurement. That's right, proper measurement. So we'll get the voltmeter out. Of course, you can see that what I'm doing to keep my brain in good shape is not working, as evidenced by the numerous videos of me doing stupid things here. So we're going to want to read the voltage. I'm using this meter because we want to read it in an ungrounded situation here. So we'll be looking for probably 10 volts or something, or nothing. So I'll put this on 60. Practice. The cathode was 8. 8 is here. Well, it's right across the 1200 resistor. Is that right? No, that's not the grid. That's almost to the grid. The grid's over here. So I'm doing this. I'm reading that. And I want to put the negative. So the grid relative to the cathode. So we'll put the negative on the cathode and the positive on the grid. And we'll read it and weep. Here we go. Everything ready? I'm ready. Everybody ready? Cats ready? Give it just a minute here to warm up. I think we got to do this with the proper voltage here. Okay, we're at 110, 111 volts. Good. On the cathode. On the grid. Minus 6 volts. You couldn't ask for something nicer than that. So what about that resistor I just changed? What does the book say about the bias on this tube? And 6S, QRS, 6S, 6J. Well, I am losing it here. 6J5. 6J5. Maximum ratings. Characteristics, where they got typical operation. They don't say that. Okay, well anyway, here it says, it doesn't say. up here. Characteristics. Grid voltage. -8. -8 volts with a 250 plate. So we're in the ballpark. Ooh, what's down here? Grid voltage for plate current of 10 microamps. -18. We don't know what it was when I had the original resistor in there, because I did a false test which caused a false reaction and a false change. Although oddly enough, I discovered something weird in the radio. This really high valued resistor doesn't look like any other resistor. Mystery. It's a mystery. I think we should probably play this radio and make sure it's still working. Is that just a matter of turning up the volume and setting it on radio? This is broadcast. I'll be the antenna. Oh yeah. I think it's working good. I think that's all we need. Okay, either I'm done for today or we're going to look for another capacitor. I have to decide what I want to do. Power off, Jim, power off. So if I tell myself what I'm doing is I'm getting the radio ready for the first run through the alignment tomorrow, then there's a couple more capacitors I should really hunt down, and those are ones that are responsible for quieting screen circuits, like this one. 10 microfarads. Wow. Ooh, okay, I wasn't expecting that. This is probably part of the 3-part capacitor here. It's probably part of this. This is C31, C30, and this is, no, I can't read that. So that's interesting. We got to find this, where this is. And then, you know, here's another one here. That might be important. Also on the screen circuits. So they're using an electrolytic one here, and they aren't terribly good at higher frequencies. And maybe that's why they've also included a regular wax one here. So probably finding these two, it would be important. Now there's more screens involved here, isn't there? Like here's a screen. No, it's the same one. Same screen over here, but this is a different matter by the time you get over this far. So yeah, so this is it. So it's this guy and this guy. I should find these two capacitors, and at the very least this one for sure. Let's find this one. This is C, looks like C6. The parts list. Who's got the parts list on one of these pages? Parts list C6. There we are. 10, 30, and 15 microfarads. That's the filter capacitor. Wow, that's not very big. Filtering. Okay, I just looked away for a minute, and I looked back. I don't know what I'm looking at. Here we are, C6. So we can just cut this one off. It's a 200 volt, but it's not going to sustain 200 volts. It's a 10. Why would I worry about this? Why am I worried about this? Because I'm thinking this isn't working well. How do I know this isn't working well? The radio's not humming. These guys seem to be working well. Why am I thinking this one is not? There's no. So if it's not working well, the big capacitor like this, in that position, we would get a lot of weird stuff going on in the IF, where the strong signal coming out of the IF manages to get back into the start of the IF circuitry, and you get the howls and motor boating and all kinds of weird stuff can start happening. None of that's happening in this radio. I think I'm just going to leave this for now. And what about that other one? The other one, would be this one, C20. Maybe we should find this one. C20. Okay, where would it be? It could be almost anywhere, somewhere around this tube. No, probably. It could be anywhere. C20, right? C20. No. C20 somewhere in here. Does anybody see a C20? Just hunting around all over the place. Well, I will. Here it is. I found it. I was going to say, well, I'll find it. Here it is. C20. One side. So C20 is attached between terminals on this tube. Now, I can't really see what's going on in here with the. So C20 was one leg to ground and the other leg on the circuit that carries the voltage to the screen. And so this would be the grounded leg, and this would be the other one. Okay, let's look in the radio and see if we can spot this. In fact, I'll put this on my screen. I'm going to look myself and say C20. I think I see it. Okay, let's take a look. The big thing sitting right here. Now, just to be absolutely sure again, let me just put this back on my own screen here. So C20 should be coming from that terminal, and on that terminal should be a big resistor, 22, this one here, that's it. So this is definitely the right capacitor. And it goes across and connects, yeah, that's it. So this guy looks to be in really good shape, but looks can be conceiving. Conceiving? I guess they can. Looks can be deceiving. I'm going to replace this anyway, so let me... Cutters, please. Again, I don't remember any symptoms in the radio. We're going to use this guy. And I mean, we can bet that this capacitor is leaking to some degree. It's not like new. And this tester I'm using, it really is dependent on it being in like new condition, I think, to get an accurate result. $17 nanofards. Does that ring a bell? What's going on here? This is a perfectly good, like new capacitors. What's going on with this guy here? 104K. It says 17 nanofarads. So this is 99 nanofarads. Now maybe I'm not thinking about this right. So this would be the same as a 100 nanofarad, which is a 0.1 micro, which I think is what this is. Am I just confusing myself? Did I say something about Sudoku? I better start playing Sudoku. Maybe that would help. I mean, I just... Okay, so 17 nanofarads is a 0.01 or a 0.02. And this is a 0.01, I'm pretty sure. Where did I cut this from? I cut it from over here. Before I forget, when you see some of these terminals chained together with a bare wire, it's usually indicating that's a ground. They're all grounded to the chassis. The purpose of the clip lead is to make it more difficult for me to forget where the replacement goes. I like a challenge. two wires there. 0.01. Okay. Let us step over to the other side of my little shop here. Can't get this somewhat stable. You get a closer look. Okay, capacitor is connected. We're at, if you can read it, it says 25 volts, but it actually puts 50 out on this setting. It's not opening all the way. If you go to the next voltage up, I'm sure it won't open. So when they're in this state, you really can't measure, I find anyway, you can't measure the effective capacity. And whoa, camera gone wild. You know, is this leaking enough to cause a problem? Screen currents, screen circuits are pretty strong, so probably not. We'll stick a new capacitor in there anyway. The extensive destruction in my house has come to a stop as the cats are taking a break. There's one. Bird, what are you doing? Resting up for the next round. With my brother. Yeah. Okay, so what we're going to do is we're just going to play this radio at this point and reassure me that it's still working. I haven't disrupted it too much. We'll grab this here. We're going to put it on an antenna and let it do its thing here. I'm going to leave it upside down because it's a hassle trying to get right side up, upside down. Everything looks good. We can still tune it. Good. Okay, volume down. Switch is on. Okay, and did I connect the antenna? Did I actually connect? I did not. I did not actually connect the antenna. Well, let's do that. So ground goes there. Antenna goes here. The band we're on, I think that's phono, I think that's broadcast. Here we go. In the meantime, okay, radio. Pretty quiet. Sounds good.
Twisted in ways you won't believe, but Charlie's instincts never fail. A thrilling new season of Poker Face now streaming exclusively on City TV Plus. Sportsnet 590, The Fan.
So this is the one of the two strongest stations I can pick up, and a good radio. This would be just the sound of the program and none of this hissing stuff going on. Probably because of bad alignment, but I'm not sure. We're feeding this with, well, it's a little low on the voltage. Let's put it up to more proper voltage. This is garbled up, I think, because there's an interference signal right on top of the. But most radios, I think, would do better with the station signal. This is getting quiet as we go up, 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 getting quieter and quieter. A short rate at the end. Okay, we'll go to another band. Ooh, lots of volume. I think there's a lot more volume than there was. And band up, band up. So we're on the top band now, which is possibly has some stuff on it. Oh boy, hit that short. Wow, that's loud. So all that stuff, I always imagine that's an external interference of some sort on my antenna, and it's just repeating every few kilocycles because it's actually a very low frequency thing with many harmonics. That doesn't make a lot of sense, you know. But you know, not making a lot of sense has not stopped me in the past. Getting quieter. Somewhere down here there should be a station. There it is.
Because he literally was. He was conceived in Mary's womb when the spirit of Yahweh overshadowed. These miraculous events that have been prophesied almost 1,000 years before. Let's go there. Let's read our last verse there, Psalm 2, verse 9.
Good volume, but let's not go there. Let's not read. Let's not try turning it off with the wrong knob. Okay, the radio has survived another day in my shop. I think its performance is going up a little bit. I think I'm in a position now where the next sensible thing to do is do an alignment job on it and see what that does to the radio. Yeah, so that'll be tomorrow. Tomorrow we'll just do the alignment and see what we get. Thanks a lot for watching today, and go have yourself a nice day. I'm heading out for the my wood pile. Can I show you the wood pile? Depends if my camera can accommodate the bright light that's out there. Let's see what happens here. Okay. Scared my cat. Well, I'm not sure it's going to do the trick out there, but there's a big pile of wood. Gigantic pile of wood from the ice storm disaster. That every day you can hear chainsaws going here and there out there still. Big tree was cut down just a couple days ago out in the right-of-way here because of whatever reason, I don't know. It was a big tree. Anyway, so okay, once again, have a great day and see you on the next video.